All right, so this time we'll take note of the R type data part, right? Yes, and with this one, we hope we understand the whole movement of instructions better, right? So the R type data part, for example, if you are given the instruction add into T0, T1, and T2, right? So it means that your destination is for T0, your first source is for T1, and your second source is T2. Now, the procedure you take is this: fetch the instruction and implement PC. Now, something like this. Every instruction will do it. It's constant, right? It's constant for every instruction. Now, the second part is input dollar, input T0 and T1 from the register file. What he's saying is that decode the instruction. And decoding the instruction means that just applying, let me see for the, yeah, just applying the correct uh, line signals, right? Towards reg 1 and reg, like the read ones, right? So this one you apply maybe show me register 1, right? And it show me maybe the content stored in register 1. That's the register specified in the instruction, source 1. And it will split the content here. Show me the content stored in source 2 and to split the content here, right? So that's basically it, right? And so this one is just like the decode. And the second part is like the ALU operates on what? The instruction sources, right? It's supposed to be what? T1 and T2, right? Not T0 and T1. Yeah, I think it's supposed to be T1 and T2. Per the func field of instruction. So depending on the func field of the instruction, right? Now, when it is transpiled, you know that there will be this one will be given a func field, right? When it is converted to how do you call it? Assembly the machine language format, this will be given some func field, right? And that will show that it's an add instruction. Now the result is written from the register file using bit what 15 to 11, and we saw why it's 15 to 11 in the earlier video. So that's basically it. Now we can go to the same steps for load word, right? So I told you fetch and implement piece is the same. Read the register file, it's also the same, right? Now how do you call it? Yeah, this is fetch and this is decode, right? So you basically do the first two steps in all instructions, but for the first one it's constant, but for the second one, depending on the instruction, you have to do it a bit different. So for example, here you read the register file value, right? And this time it will be the base address, right? And the next part is that ALU adds value from what? $T2 to sign extended 16 lower bits, right? So this is what they're actually meaning. So this is what they mean that like while we are in the decoding stage, right? The 16-bit immediate field, right, will be sign extended, right? But I mean this one didn't state explicitly. Then the result from the ALU, right, is equal to the address to the data memory. Always remember this. Load word is going to fetch data from memory, right? And how is it going to fetch data from memory? We have to get the effective address, right? So the first three steps for the first 3 steps was to get the effective address actually, right? Now the next step is now we have gotten the effective address, you can use it to what retrieve from memory, right? And rewrite it back, right? Yes. So just conceptualize it. So you realize that when you combine the R format data type and data part and the load store data part, you get this. You realize that the R format data part only ended here, right? Something like this. But with the load web format data, yes. So you have to go to memory and have to write it back. So that's the only thing you have to indicate. Now, think we could show some animation, right? But this is static, so we have to. So let's take time to go through, right? Now you realize that for our type instruction, we needed 3 registers. Remember, we needed RS, RT, and RD, right? Forgetting about the shunt field and everything. We needed 3 registers, right? And now those 3 registers are what you actually see here, right? So those are the 555 you see here. So they'll be applied to the read input of the register file, right? And um, the registers, two of them are source operands, right? So the output will be read, right? And they'll be put what onto this line, right? Which will be supplied to the what ALU. right? Now after they are being supplied to the LU evaluates them, right? Now the output will just flow to the multiplexer. And now mem to reg will be what? Assigned zero, right? Will be assigned I think it's is here is zero and the top is one. Oh, okay. But you like usually when they give you the question, they'll write it, right? So that you know. So you assert it so that this one will be selected and to be written back to the register file, right? But how will it be written back? Like what address will be specified in the register file? That is what the use of the word third operand, right? So that's the use of the third operand. Now, the load store data part is also no different, right? Now, although you see anywhere you see a wire or that black lines, it actually means that like how do you call it, signals are flowing through them, right? The only thing which stops them from being evaluated are those multiplexers which select some signal over some signal else, right? So it means that even for the load word instruction, this 5 bit part, right, will still be applied, right? By the end of the day, it will never be used, right? So you realize that we'll take the 16 bits immediate, right? Sign extend it to 32 bits. Then we also take what one of the source operand, which is actually the base address. We add it into the ALU, right? We add it into the ALU to get what the effective address. Now we read from the effective address, but this time we don't select the lower one because what we are reading from memory. So read from memory and what come and store it back, right? So just watch this diagram a lot of times and play the animation as much as you want. You will conceptualize. Store data part is no different, right? Remember, store will actually take from register file, put it into memory, and that's all what you see. So you realize that here, check, store did not assert anything for the right, this one. Like although it will be applied, at the end of the day, will not assert read write to be zero for store, right? Will not write to the register file because store does not write to the register file. It reads from the register file and stores into what memory. Right? So that's what store does. Right. So it means that here, even if you specify anything, it will be useless. Right. But the reason why the diagram is like this is that still the wires are connected. You see, we can't change it's like not like every instruction we'll go and change the connections. Every instruction no. We'll use multiplexers to what like silence the ones you want or allow the ones you want. So that's all what you have to do. So we'll specify two addresses, right? One for the base address, one for the should I say destination address, right? Now we'll use that base address plus the 16-bit field towards sign extend 32-bit field, right? And the source register address, right? Would read that register from the register file. So maybe when we read it, we got a value 5 from the register file. So that 5 is what was we're going to store in memory. So in this time here, memrise will have to be 1 so that we can store it, right? So it's actually no different from the other instruction, but depending on the different control signals, we're doing different. So that's what you have to take note of. And this is the full data part, right? This is the full data part. And there are few notes you have to take off. There are few things you have to take note of. Separate instructions, memory as instruction and data, read okay in the same clock cycle. It's not anything much of new information. Branch data parts, yes, it will also not be different, right? You fetch, you read the register, you subtract, you assert if it's zero, you take the branch. If it's not zero, you don't take the branch, right? Any question? So that's similar thing for the branch data part. So the branch data part, we update our original data part with just this small part, right? Which will calculate our branch target address for us, right? And yeah, with that, I think we are done with it. So there's a question. It says, is the mem read signal really needed? Think of read write. Is it really needed? Let's see. Um, mem read. Okay, read write is needed, right? Because we can't be made to write to the register file anyhow.
I know they won't.
Yeah, so yeah, I believe then memory will be needed, right? And so that we know exactly when to read from memory, right? And to allow the data from memory to be um, latched on, because this is a single cycle thing, and you can't have a contention if you are reading and writing at the same time to memory. Yeah, yeah, but I'll look into that. So for executing the add, this the data part. I think we've already seen this. Load words, we've already seen it. No different.
The part we use, right?
The
The top one.
the top ones.
This one.
Yeah, yeah. These ones they
Yeah.
are for implementing the program counter. So they are always in use because after every instruction, implement the program counter. So they are always in use. Yeah, they are
I'm
always
not
in.
doing that for how the program affects.
Oh, okay, okay. So the program counter first, you fetch the instruction, right? Now single cycle data part in the same cycle, right? In the same cycle, the instruction, the instruction, you fetch the address of the instruction from the program counter. So the program counter is a register. You fetch the address. Now the same address you fetch in the same cycle, the other adds four to it, right? So this is like the next address of the next instruction. Now, if it is not a branch or jump type instruction, right, then you select what PC source as what zero, so that your program counter will not be like will not add anything to your program counter like the PC plus four, right? We'll only use the PC plus four as the next, so we execute the next instruction. But if maybe it's a branch or something, then we would come and add again and select the right part. So that's for the program counter. Nothing new. And yeah, that's also for the branch instruction. Yeah. And I think with this, we are done with it, with the data part. So there is also not much difference of the branch instruction, except that the branch instruction was most important is where you go and pick your next program counter value, right? And one of the important aspects is this ALU zero, right? If it's a branch equal instruction, the branch is it compares the two registers and they are the same, right? And the branch is taken. It means that here will end up being one, right? And it will be fed into it and um to be used to take the right part. So it means that that one you come and select what the lower one instead of the higher one, right? So that's the only difference in the branch instruction. So control, when you try to control use the control signals, realize that so far we have a lot of control signals, mem write, mem read, ALU sort, mem to reg to dist, like a lot of control signals. Now we need a systematic structure, right, to be able to get the control part, right, so that it will be a bit simpler, right? Now one common solution is to use a PLA, right? And how will you use a PLA? Remember the PLA has what an end gate and an outside. You probably forgotten your PLA, but it's nothing much. So, for example, this PLA, right? Let's take F alone, right? So let's take F alone. When we take F alone, you realize that F is currently is from only this one,
Yeah.
right? F does not feed into any OR gate, so F is from only this one, and this one is what A B C. There is no bubble here, so it means that what F is what A and B and C, A B C. Right? Now when we take E, realize that E is from what here, right? One of E is from here, and that one is also what A B and not C. So this will be A B C bar, right? Plus we'll come and also consider this one. That one is also what A, B bar, C bar. Plus, we'll come and consider what I think we've done one, two. So the last one, right? That's what A bar, B, C. So it's not really too difficult to translate, right? But this one is simpler because to help you to easily translate from either like it will help you to not use plain logic gates. You can reuse the logic gates, right? Right, so that the control will be simple. Now we want to extend the data paths. So far, what we have done can only execute branch, it can only execute I type and R type instruction. Now we want to execute jump instruction, right? Jump instructions, this is how they look like. Um, a jump instruction will have the opcode and another 26 bits specifying the target address. Right. So that's jump instruction. So 6 bits opcode, 26 bits address, which is what 32 bits. Right. Now, when we want to calculate the branch target address, right? The jump target address, there's a difference between branch target address and jump target address. So jump target address for jump instruction, branch target address for branch instruction. So we know that the upper bits, 31 to 28, right, will come from the program counter. Let me show you practically. So this is what they actually mean, right? Um, Now, when you are doing jump instructions, right, the question says here says take you see that the target address, the program counter is 32 bits, right? Now you are jumping to another address, right? That address also has to be 32 bits. However, the jump instruction only has 26 bits, right? It specifies a 26-bit address.
Okay.
So it means that we have to extend it towards 32 bits, right? Now, unlike sign extension in other ones where we just put zeros for this one. This one you have to be careful because you are moving through the program. You are moving through the program space. So the first thing is that you make sure that the upper 4 bits, right? The upper 4 bits of the instruction are from the program counter. So remember that we increase the program counter by what? By 4, right? So that PC plus 4, right? The first 4 bits of that PC plus 4, right, will be used for the first 4 bits of the jump instruction, and that's what from 31 to 28, right? And it will like be joined to it. So that's what you see. It has been joined to it, right? So the first 4 bits will be used for that. Now, the next thing is that you realize that um the bit 27 to bit 2. Now this is 26 bits long. 27 to 2 is 26 bit long. That is the same thing we specified in the instruction. You see, I said we specify um, jump to maybe an address. The address will be 26 bit length because the first 6 bits will be used for opcode. The remaining 26 bits will be used for what the address you want to specify.
Yeah.
However, we have to extend it towards 32 bits because we are jumping to an address. So we need a 32-bit address. The first 4 bits of the address will come from what? The program counter, the first 4 bits of the program counter. Now, the next 26 bits will come from that 26 bits in the jump instruction, right? And we'll store it what in from bit 27 to bit 2, right? Now the last 2 bits are zeros. Why? MIPS is what? Word aligned. So when you put 2 zeros in binary, that's one shortcut. When you put 2 zeros in front of any binary number, it becomes divisible by 4. So if I have 101, I put 2 zeros in front of it. It becomes 1000, 10100, right? That's divisible by 4, right? So um, that's why you remember that the earlier slides, they said something like when you correctly that how do we call it? When you are doing when you are doing branch or jump instructions, right? The target address divided by 4 before you put it in the immediate field. Do you remember something like that?
Yeah.
And that's because the last 2 bits will pad it with zeros, right? So don't make it something which is don't put the whole times 4 value there. You like divide it by 4 before you put it there, right? We'll maybe see an example of that, right? But that was said in earlier chapters of these lines, right? And the reason is this one because the last 2 bits is said to be 0, right? Now mux controlled by jump address select yes the jump target address as the new PC, and maybe when we see the data part we'll see. So the mux will select I think the one at the PC source for jump instruction. And this the formats the how the formats look like. So if so far we've been looking confused about the instruction format. This is how it look like. So yes, from 0 to what 26, right? And from yes, from 0 to 25, sorry. And from 26 to what 31 is what for the opcode, right? So always 26 to 31 is for opcode for all of them,
Yeah.
right? And from 0 to 25 for jump It is for the target address, right? And that's why here is what from 27 to 2, right? So that's where it will be stored. 27 to 2, it is also 26 bits. So that 26 bit is what you see. This 26 bits.
Yeah.
That is what will be stored. And the upper 4 bits will come from the upper 4 bits of the program counter, right? Then the last 2 bits will be what's padded with 0 to get the effective jump target address, right? So maybe you can get a question to calculate the effective jump target address. You should know what to do,
Okay.
right? You should know what to do. The value they will give you here, the value they will give you here, right? Write it down. So um, write it down, and it will be 26 bits long,
Yeah.
right? So you put the whole 26 bit value down. Now go and check your program counter. What is the first 4 bit of your program counter? Come and put it here, right? And add 2 zeros at the end. That's all. If you evaluated the jump target address.
Okay.
Uh-huh.
It came to you now. That's all.
Yes, when they give you the jump target address in hexadecimal, I would advise to change it to binary first. Yes, change it to binary. So change everything to binary and do it because these 2 bits are what binary. That's that's it for that. I think yeah, this one is also quite understandable for the jumps. Now they've extended the data part to do jump, right? So the first part, this one would try to see if you are doing branch. This one will try to see if you are doing jump, right? And this is some kind of, should I say, if else, right? So, first, this one is just PC plus 4. What is coming as PC plus 4? Now, if we are if we are doing if we are supposed to do jump, right? This PC plus will not pick PC plus 4, right? We rather come and pick the sign extended evaluated jump target address, right? And that's what you see. And it will go back. And the diagram is not clear. So that same diagram, that's what you see, right? So if you are doing a jump instruction, right, the mux one here will be selected, will be highlighted, right? So that mux would enable us to pick from here, right? Instead of taking from either branch or PC plus 4. So this lower one is either branch or PC plus 4, right? This higher one is what only jump, right? And that's that's it for all. So the remaining instructions are being executed step by step, and I think by now you should know what happens in each instruction. Yes, that that will help you. And yeah, maybe we would make a separate video on this one, how to solve this question. But for now, it's okay.